we'll see Archimedes principle and how it can be derived from work energy theorem. So what is an Archimedes principle? It tells us how much is the buoyant force acting on any object immersed in a fluid, partially or completely. So suppose if I have a container having some liquid or some fluid in it, let us say rho f is the density of this fluid and an object is immersed in this fluid. Let us say it is the object, so let us say rho o is the density of the object and v is the volume of the object. So Archimedes principle tells us how much will be the buoyant force acting on the object due to the surrounding fluid in the upward direction. So how much is that force according to Archimedes principle? We have to see how much is the weight of the fluid displaced by the object. The weight of the displaced fluid will be the buoyant force. Okay, so the buoyant force that will act upwards on this object will be nothing but the weight of the displaced fluid. So I'll just draw the displaced fluid over here. So the volume of the object is V. So obviously it will displace or shift aside, you can say. How much volume of fluid? The same volume as that of the object. So this is the so this over here is nothing but what? The displaced fluid. Okay. So as is this fluid is the same fluid which is displaced, so it's displaced. So its density is nothing but rho f, and what will be its volume? The volume of the object. What will be its weight? It will be mass of the displaced fluid into g, and mass can be written as density into volume and multiplied by g will get the weight. So this is nothing but the buoyant force. So the Fb over here, the buoyant force or the upthrust acting on the object in the upward direction, will be equal to rho f into v into g. This is the buoyant force acting on the object in the upward direction. Let us Let us derive this from work energy principle. Okay, see how can we do that. So I am taking the same scenario. Only thing is that suppose this is the fluid, this is the surface of that liquid, and let us say density of the object is greater than the fluid. So it should like go inside and sink in the fluid. But I am suppose there is a string attached to this object which is holding the object, and the object is not just being held, but suppose this is pulled up with a constant velocity. So the object is being pulled up with a constant velocity. Very good. What are the forces acting on the object? It will be the gravitational force, that is mass of object into g acting in the downward direction. The buoyant force will act in the upward direction, and the tension in the string will also act on the object in the upward direction. Now, since the velocity of the object is constant, the net force on the object is zero. So the total upward force is equal to total downward force. So we can say T plus Fb, that is the buoyant force, is equal to m naught g. So T will be equal to what? We can say it is m naught g minus Fb. Okay. Yes. Again, rho naught is the density of the object and V is the volume of the object. Okay. Now, one of the consequences of work energy theorem is that the work done by the external agent is equal to change in potential energy if change in kinetic energy is zero. Now, since it is being lifted up with constant velocity, so the change in the kinetic energy of the object is zero. So this formula is applicable. Now let us see the work done by the external agent. Now external agent is the one that is pulling up the string. So the work done by the external agent will be force into displacement. Yeah. So let us say that the object moves up through a distance of h. Now let us say it is still in the water uh, when it has moved up to a distance of h. It is not halfway inside the water and halfway outside, not like that. Let me redraw this diagram. So let us see. Okay, we have the surface till here. Okay, so the object is moved up through a distance h. The center of mass of the object has moved up a distance h. So how much will be the work done by the external agent? Force into displacement. So it will be T into H. And what will be the change in potential energy of the object? The potential energy of the object will increase by amount mgh, mass of object into g into h. But apart from that, since the object has moved up, the surrounding liquid has moved down, right? I mean, the surrounding liquid will fill up the space of the object. So we can say that as the object moves up, effectively, the water over here will come down and take up the space of the object. Effectively, that will happen. All right. So, so the water or the liquid uh, having the volume equal to the volume of the object has come down through height h. So it has decreased its potential energy. So the net change in potential energy will be increment in the potential energy of the object minus decrease in the potential energy of the fluid. So how much is the decrement in the potential energy of the fluid? It will be mass of the fluid that has come down from up into G into H. Right. So all the H will get cancelled. So T will be equal to what? M naught G minus now mass of the fluid that has come down can be written as density into volume. So density of the fluid into volume of the object. That will be the same as the volume of the fluid that has come down effectively into G. Okay. So if I compare the above equation of T, equation number 1 with equation number 2, what I will get directly that if I do compare 1 and 2, the left hand side is same, so right hand side has to be equal. So in that m naught g and m naught g will get cancelled, even minus and minus n will get cancelled. So the buoyant force has come out to be equal to rho f vg. So that is what we had seen here. The buoyant force is rho f vg. So this is how we have shown the Archimedes principle by making use of the work energy theorem. Specifically, this formula, work done by the external agent is change in potential energy if the change in kinetic energy is zero.